Okay, we've been discussing whisper theory, valence shell electron pair in repulsion theory. So we'll now move on to something called valence bond theory, and further on we'll do molecular orbital theory. Now we know that in this whisper theory, the bonding, the chemical bonding occurs as a result of the lone pair of the valence electrons, and hence the name valence shell electron pair in repulsion. Because of the presence of the valence electrons within an atom, it is being shared or transferred uh, with another atom, and then because of the sharing of the electrons, a bond is formed, and hence whisper theory. But there are drawbacks in this whisper theory. Now in valence bond in whisper theory, we know that the bond formation is due to sharing of electrons, which gives us a covalent bond. But this does not give any idea about the bond dissociation entropies or the bond lengths in different molecules. So the simple picture of like the covalent bonding gives us no idea about the shapes of polyatomic molecules. Therefore, to overcome these limitations, valence bond theory was adopted. Now, before moving on to valence bond theory and molecular orbital theory, I want to share something. This these valence bond theory and molecular orbital theories, they are usually used for computational purposes in computational chemistry. Computational chemistry. This computational chemistry is where you plug in all the information of bond lengths, bond densities, electron density, everything, and then you plug those values in a computer, and then it'll try and generate the whole molecule. Of course, these days we no longer use this valence bond theory in computational because there are so many limitations. So we have adopted again another theory, which is our molecular orbital theory. So that's the that's the thing I wanted to tell you before we start valence bond theory. Now, there are some assumptions in valence bond theory. Now, it's given in your book, but the basic idea of valence bond theory is that in whisper theory, it's simply sharing of electrons between two atoms and thereby forming or giving us a bond between the two atoms. But in valence bond theory, um, we shall see that sometimes there will be the transfer of electrons from one orbital to the other, and then mixing up of orbitals, or simply called hybridization. Hybridization, it is a concept, hybridization. So due to hybridization, uh, the process of formation of bonds varies. Like we'll talk on at length later on about hybridization. So that is the main idea, or the main idea behind valence bond theory. Now, this valence bond theory, uh, the central ideas I've been saying is thinking about the electron pair as the crucial component of a bond. It's similar to valence shell electron whisper theory. Now, but it is it has included promotion like promotion, hybridization, resonance, and so on, which we still, of course, which are still part of molecular orbital theory. Now, this valence bond theory, it mainly focuses on single bonds, so it is more widely used in organic chemistry, because in organic chemistry we have got these big molecules, and you really want to focus on the carbonyl group. So for example, a localized description, which is characteristic of valence bond theory, is typically used. But in organic chemistry, we have got little molecules of fairly small complexes and so on. So you have to think of the electrons being distributed all over the molecules, and so we adopt the molecular orbital theory, and is rather more natural as a way of talking about these type of systems. Now, in valence bond theory, we have to think of electrons in orbitals and let them overlap between the electron pair, and then you've got a bond. It forms a bond because of the overlap of the between the electron pair. Now, it's related to Pauli's principle, not our Pauli's exclusion principle, but the more general Pauli principle. Because only if the electron pair their spins, then thus the two overlapping orbitals form an overlap of wave function of the appropriate symmetry, like uh, in as the Pauli exclusion Pauli principle suggests. Now, but then we get into the classical case of carbon. Why does it form four bonds, suppose, in methane, or two bonds for ethane? So we invoke the idea of promotion of electrons to the excited state, where we'll see that in hybridization. Then you realize that all four bonds in methane should be same, because but but incidentally they are not. And so then we introduce the concept of hybridization, and then you get to the point where you realize that there are several possible structures that you can write in a valence bond form. So you introduce the concept of resonance, which distributes bonding characteristic over the entire molecule, and also helps to lower its energy, because to form a molecule or to form a bond, it has to be at the lowest energy state. Then only we get the bond formation. So we'll get to hybridization. So what is hybridization? This concept was given to us by Linus Pauling and Slater. These are powerful scientists. Pauling was in fact the one who introduced the idea of a double helix. Of course, later on it was confirmed by Watson and Crick, but Pauling gave the concept. Now, in this hybridization, there are assumptions like atomic orbitals, the atomic orbitals, they combine to give a new set of equivalent orbitals known as hybrid orbitals, and that process of intermixing or combination of between two atomic orbitals is called as our hybridization. So suppose an s orbital and a p orbital, if they mix up, they no longer behaves as an s orbital or a p orbital, but now they are hybridized. We call it as sp hybridized orbitals, and they form a bond, a chemical bond. So suppose to understand the idea, hybridization. Suppose we have, let's talk about methane, CH4. Now, in methane, let's look at the electronic structure of carbon. Electronic configuration, 1s2, 2s2, and 2p2, because carbon has 6 electrons. Now, I've already told you that these are our valence electrons, so in the ground state are 2s orbital and 2p orbitals will have paired electrons. Pauli's exclusion principle, that two electrons cannot have the same spin. It has to be of opposite spin. And then we have two, but Hans Paul's rule, Paul's exclusion principle. We have to fill simply first, and then after that on the pairings, electron began. So in two p orbitals with two electrons, so they'll have they'll have one electron in each of the orbitals. So this is our ground state. But when it is excited, in the excited state, one of the electron migrates to our p orbital, gaining energy, and then now we have 4 electrons in the 4 unpaired electrons. So we know hydrogen has 1 electron. So each hydrogen will come and pair with 1 each of the 4 carbon electrons. So now we have, so this is our s orbital, this is our p orbital. So we have an 1s and we have 3 p's. 3 p's. So the hybridization of methane is sp3. That's how we write the concept of hybridization. So now in carbon, all the 4 bonds in methane, all these 4 bonds are sp3 hybridized. They are no longer an s bond. They no longer show an s character or a p character, but sp characters, sp3 characters. All the 3 bonds have sp3 hybridization, or they are sp3 hybridized. Now, when we talk about the methane, the bonds between carbon and hydrogen in methane, we have single bonds, sp3 single bonds, and these single bonds are called as the sigma bonds, and denoted by the Greek letter sigma. But what about say C2H4 ethene? What is the hybridization of carbon and ethene? Now, for say the first carbon, both the carbon will have the same valency. So we'll just write the excited state of each carbon. So excited state of carbon 1 will have 4, and then for carbon 2, we have 2 carbons, so we'll have the same configuration. Now, but we only have 4 hydrogen atoms. So this s orbital, we have p. So these 2 s orbitals, they'll share the electrons and form a sigma bond. And then the 4 hydrogens will enter symmetrically. H. So 4. And these 2 p orbitals, they'll overlap. Now there is one thing you need to know about p orbitals. We know that p orbitals have dumbbell shape. So When two p orbitals come and form bonds by head-on collision, then we get a sigma bond. But if they form bond by overlapping sideways, then we have two point of interaction. So this gives us our pi bond, pi, the Greek letter pi. So this is what happens here. Now, therefore, if we write the structure, or if we represent this type of structure, the ET, then we'll have these two will give us a single bond. This overlap will give us the next bond between the two carbons, and then these two hydrogens will be symmetrically placed on each of the carbon atoms. So if there are more than one bond, then the additional bonds form or gives us the pi bonds, and so one of them will be sigma bond and the other one will be a pi bond, and that's the difference between sigma bond and a pi bond. And one thing you need to know is that these sigma bonds are really strong. The interaction between the two electrons are very strong compared to our pi electrons. Later on in your further studies, you'll also notice that we'll have delta bond also. I won't talk about it now, which are metallic bonds. So I forgot to mention, so that one in ethene, the s orbitals forms one sigma bond, and then we have these four hydrogens in the p orbital, and this is our overlap in case of ethene. So here the hybrid, since this one is just the overlap of orbitals, they are not considered to be involved in the hybridization or mixing up of orbitals. So because these two have similar in energy, so now we have one s orbital and two p orbitals that are involved for this particular compound. So sp2 hybridization. We call it as sp2 hybridization for each of the carbon atoms. But each of the carbon atoms in ethene is sp2 hybridized. Okay, now let's move on to ethyne. C2H2. So similarly, we'll have the excited states of each of the carbon atoms. And then we'll get a sigma bond from the s orbital. And then we have two hydrogens, so symmetrically they'll enter for both the carbons. And then see, these two p orbitals, they'll overlap each other. So now we have two pi orbitals. Now, since only one s and one p orbitals are involved in mixing up, therefore, this in ethyne, the hybridization of carbon is 1s and then 1p. So sp hybridization. And these two pi orbitals, let's represent this. There are two carbons, and then we have one sigma bond, and then we have two pi bonds, and then we have another two sigma bonds on each of the carbon with the hydrogen. So we have two pi bonds and one sigma bond. So this is how ethane looks like. The hybridization is sp. So I hope you have understood the concept of hybridization. So you can try for simple molecules like ammonia, carbon dioxide, find out the hybridization state of nitrogen and carbon in both the compounds. I want you to first predict the structure of ammonia as well as carbon dioxide from the Whisper model. So the Whisper theory will give you the prediction of the molecules, whether it would be linear, diagonal, tetrahedral, octahedral, and so on. So try to predict the structure of what the, and then the hybridization state from valence bond theory. So you understand more if you practice. Now let's move on to, before moving on to molecular orbital theory, I want you to, we'll try to establish an example why we need to invoke molecular orbital theory. So we'll try to predict the hybridization of phosphorus pentachloride and nickel tetracyanide. It is an ion. So if we try to predict the hybridization state of phosphorus pentachloride, and we know that phosphorus has 3s nitrogen phosphorus. So it has 5 valency. Valency is 5. So in the 3s and 3p. So 5. So 1, 2, 3, 4, and 5. So this is 3p. So this is our phosphorus in the ground state, and in the excited state, 1 electron will migrate. Now, in phosphorus, in the excited state, this one electron from the s orbital will migrate to a higher orbital, but here it's already symmetrically placed, the electrons. So what happens? We know that in phosphorus we have empty 3d orbital. 1, 2, 3, 4, and 5. So we have empty 3d orbital. So this electron will migrate to the empty d orbital. And so this is our excited state of phosphorus. Now this chlorine has a valency of 1. So each chlorine will enter or pair up with each of the electrons. So now in PCl5 we have 1 s orbital involved in the hybridization. We have 3 p's, and then we have 1 d, only a single d. So the hybridization is sp3d. What about nickel tetracyanide? So what is the valency of nickel? So nickel is D8. So we have 4, 6, 8, 10. We have 10 valency. So in the D orbital, 1, 2, 3, 4, 5, and then 4s, 3d, 4s. So 1, 2, 3, 4, 5, 6, and then 7, 8, 9, 10 valency. 3D here and 4s. So this is the ground state. Now nickel in the excited state. So both naturally this is already filled, so we cannot migrate. But in the excited state, it will migrate. So in nickel we have empty for p orbital. So one of the 4s electrons will jump to the 4b orbital. So now we have 4 unpaired electrons. So all the cyanide atoms, molecule or ions, cyanide ions will enter or pair up with the nickel. And so here we have 2D, 1s and 1p. So D2sp hybridization. So this type of hybridization where the d orbital is on the outside is called the outer sphere, and then if the d is only inside, then it's called the inner sphere hybridization. Now, valence bond theory cannot explain why this happens, why or how the outer sphere mechanism or the inner sphere mechanism happens. So in order to, so that is one of the examples why we build or we use molecular orbital theory. Now, so I want you to predict the structure from Whisper theory, the structure of diamond in graphite. You have to predict the structure from Whisper theory, and then the hybridization state of the carbon in both the compounds from valence bond theory. Similarly, sulfur hexafluoride, you need to predict the geometry as well as the hybridization state of sulfur, and then IF7 iodoheptafluoride. So this is your assignment. So my number is 70056999687. So WhatsApp me the answers. You have to use Vesper VSEPR to predict the geometry, and then by using valence bond theory, you have to predict the hybridization of the complexes. So you have to submit it by you have to submit it by 10th of September 2020. So we'll try to focus our attention in molecular orbital theory in the next video.